Hi, welcome to the Advanced Wind Turbine Oil Monitoring Life Extension webinar. My name is Michael Holloway. This webinar is going to cover the technology and case studies of Poseidon Systems' online oil monitoring systems. At the end, we'll hear from Stephen Steen. He's the Vice President of Poseidon to answer your questions. And before we get going, I want to tell you a little bit about Poseidon Systems. They're a spin-off from Impact Technologies, a company founded back in 1999. They were acquired by Sikorsky Aircraft in 2011. Impact Technologies specialized in developing innovative technologies for enabling a condition-based maintenance approach for critical military assets, including drivetrains for air vehicles, Army ground vehicles, and even Navy ships. In 2010, Poseidon Systems has been a leading innovator in developing and manufacturing real-time condition monitoring solutions specifically for fluid diagnostics. They provide an end-to-end solutions for enabling online oil condition and metallic wear debris monitoring. That results in less downtime and reduced operating costs, as well as reduced maintenance costs for their customers. Now, the vast majority of wind turbine operators, well, they perform oil sampling and analysis about twice a year, and that corresponds with their semi-annual preventive maintenance tasks. These operators, well, they rely upon these analyses to provide some assessment on the equipment life, the lubricant health, and even contamination levels. But it's difficult to ascertain the gearbox condition, because while these offline analysis is a useful tool for assessing the health of the lubricant, it can provide limited utility as a diagnostic indicator for gearbox health. These limitations of the offline oil sampling and analysis for gearbox health monitoring, well, they stem from sampling practices and the very nature of the gearbox fault progression. Wear rates, well, they're highly variable in wind turbine gearboxes with a limited sampling frequency and only a small volume of oil analyzed. The fault detection by offline oil analysis can be very unlikely. The online oil condition monitoring systems can tell us many things the way an oil analysis lab can tell us. For instance, they can examine ferrous wear debris particles and even non-ferrous particles, and these can be coming from journal bearings. Can understand how much water is in the system as a contaminant, can even understand the remaining oil life, and they can be outfitted to understand the breather health. Diagnosis and recommendations can be set, alarm limits are preset, and also adjustable according to the past data and trends. An important parameter to consider with the online oil analysis for the wind turbines is the particle analysis, both for wear and contamination. The online debris sensors can constantly monitor the levels of ferrous and non-ferrous wear debris particles as they accumulate, and the acceleration rates and total mass are calculated. The wear debris monitoring detects the mechanical component failures and continually assesses severity. There are many benefits to using the online oil analysis in your wind turbine. They include sampling can be done at any location of the system. It's relatively low cost compared to an oil analysis laboratory sample, and only contamination would be from the system itself. Sampling is almost unlimited, and there's an immediate detection of a breakdown in the oil or contamination event. This does have some drawbacks, though. The degree of sensitivity is limited to sensor technology, and there's a limited number of different tests that can be performed right now. But that's changing. It's not a direct replacement for lab sampling. Now, using an online oil analysis for determining the wind turbine health, the first thing we take a look at is the oil condition. Here we're going to examine the chemical properties that could develop as the oil is stressed. Things we could take a look at is viscosity and even the electrochemical impedance spectroscopy, and that can tell us a lot about the lubricant health itself. We also look at contamination analysis. This identifies the presence of substances that may contaminate the system, leading to failure, things like water and even particle size population. And finally, metal analysis. We can test for the metals due to wear particle generation, contamination, and even the organometallic additives that are used in the oil formulas. This provides information on iron-based alloys from wear as well. Now here's an example of oils being sent off for 140 different assets. Here we're taking a look at a case study. We take a look at the concentration of iron as well as particle count. Now if you look at the x-axis, that's the number of turbines, 140 of them. Okay, and in here, iron concentration in part per million. You can see in the alarm limit was set at 70 parts per million. We have 0.8% false alarms detected and 100% missed detections. Now the 50 part per million was a warning, where we had 13% false alarms and 72% missed detections. The lab recommended limits, 25, 14, 11 for the ISO counts, well, that exceeded every gearbox, greater than 6 and greater than 14 particle size. When we take a look at the wind turbine gearbox health example here, our first time range, the low fault severity assessment is assigned due to elevated yet relatively stable wear debris generation. The second time range, between July 1st and August 1st, the severity increases. And incidence of particle generation also increase. But if you look at the third time range, where the ferrous concentration, a rapid increase in both peaks of ferrous debris concentration and a corresponding decrease in the amount of time between these peaks indicate a greater probability of a catastrophic failure approaching. Now here's an example where we had oil samples sent off to the off-site lab during a 14-month timeline, yielding no significant findings. Here, in star number 1, we have normal ISO codes in March, but in September, our actual ISO code decreases. Now we see past the January, the ISO code under alarm limits, even after significant ferrous concentrations are indicated. And then finally, a gearbox had to be replaced. The type of systems that we're looking at here from Poseidon, they consider 3 aspects. First of which is the sensors. Various sensors are detecting various things: the viscosity, particle count, wear debris. All that information is sent over for data processing and then pushed over through a cell tower where the data can then be monitored and assessed. The wear debris sensors we're talking about are the DM4500 and the DM4600. They're considered best-in-class inductive wear debris sensors, and they provide the earliest detection for mechanical failure within the asset. These sensors are actually been retrofitted in over 5,500 systems in the past 5 years. Now, these have been selected for new wind turbines as well, and aftermarket by several OEMs due to the superior performance compared to other sensors. They work on an inductive coil metallic debris monitoring, and that monitors wear levels and determines asset health in an intuitive manner. These are considered best in class with their sensitivity, detecting ferrous particles as small as 40 microns and non-ferrous particles as small as 150 microns. And this is why several OEMs have elected to use these in their systems. It's real-time continuous monitoring, detecting and characterizing these wear events, which would typically be otherwise missed. It is the earliest detection of mechanical failure. It detects failure in earliest stages and estimates the remaining useful life. The 4500, that's a mainline bypass. The 4600, that's for the pump and filter integration. That's off the mainline filtration system going into a CC Jensen offline filtration system. Now the wear debris is established through an inductive coil sensing device. Now one or more of these coil windings are excited through a high frequency oscillating voltage. On the graph, the magnitude indicates the particle size. The particle passes through a magnetic field and creates a measurable impedance change, and the width of the disturbance represents the speed of the particle. Now the phase angle can actually indicate the particle type, be it ferrous or non-ferrous. Here's an example of life gauge overview. We're just doing more than just detecting. Here's an example where even vibration sensors can't pick up this kind of information. The wear debris is a direct measurement of the gearbox damage, and Poseidon sensors can detect flow rates and calculate concentrations. There's several life gauges indicators, and some of the key measurements would be the rate of material loss and fault severity. Now here, we can actually see the fault accelerating rate over time for failure, coming back with total ferrous metal lost. This is fault severity. This is done over a 6-month range. Here's an example of a case study done with the same kind of information we just gone over. Here, load and wear rates correlate directly with an accelerated wear rate, where fault acceleration wear rate is charted. Implemented a 33% derating to extend the gearbox life by reducing wear by over 50%. That stabilized the wear rate, reducing some average power generation by only 10%. That allowed time for that long lead time gearbox to get into place. Something along these lines? Well, this is in general between a 4 to 12 month payback period. Here's an example of a case study for planetary bearings. Now, planet bearings are difficult to detect vibration analysis early on, but they do make up the majority of the gearbox failures. The vibration systems, they do a poor job of detection in planetary bearings. The wear debris sensors detect wear faults earlier than a vibration sensor. The solution here? Well, wear debris can detect early stage planet bearing failures better than other methods. Now, it detected a fault back in June 2015. Derated to extend the life and shut down for repair 2.5 years after the fault detection. That wear debris monitoring, that enabled 2.5 years of safe operation at full power and a planned outage for repair. Normally it's 15 days here versus 45 to 60 days. So here we had 30 days of additional power. There's up-tower repair instead of a gearbox replacement, which would have required a crane, very expensive, very timely. So it was a reduced number of required bore scopes as well. We looked at the validated total savings, about $250,000. Here's another example of a case study, planetary bearing. In this case, we're looking at a rapid development of a fault. The challenge here is that these failure modes can sometimes lead to rapid failure degradation, and that's usually undetected. You only have an initiation to derate within a couple of weeks. The solution here is wear debris to detect those rapid faults quickly for immediate cost-saving actions. Now, our first event happened on February 6th. It was bore scoped on 215, derated 50%, then on to 66% to eliminate any catastrophic failures. The shutdown for repair was 6 months after that derating. The wear debris monitoring, well, that enabled an immediate detection of rapidly progressing faults. Now, our planned outage for repair, in this case, was 15 days versus 45 to 60 days. Now, that's an additional 45 days of additional power production, and a catastrophic failure was avoided. This is a significant reduction in cost. It's an increased number of findings than any other method available. Validated total savings here, $80,000. In this particular case study, we wanted to know if we could reduce the bore scope usage. The challenge is that bore scopes can be costly and varies from team to team. So here we took a look at all 15 assets. In this case, we only had to use the bore scopes on 7 of them. Because the wear debris sensors identifies the turbine's width, and without sufficient wear, there's no need to warrant a bore scope. You see, only bore scopes with wear. If there is no wear, there's nothing to see. There's no need for a bore scope. And we can actually spend as much time as needed to identify the high probability faults. This improves our quality and reduces our team-to-team variability. Now here's an example where we can understand low oil levels by looking at the wear debris generation. The customer is notified there's damage to the gears and bearings because the oil level is low. Now, adding oil, that'll allow for proper lubrication, stops any kind of wear damage from continuing to occur. Now this detection is prior to any low oil alarms triggered in the SCADA system. The debris generation ceases once that oil level is restored to the proper level. Low oil leads to improper film formation, and adding oil, well, that establishes the proper film. That reduces the wear. No other system can do this. This detection occurred prior to any low-level detection in the gearbox. Here's an example of gear tooth lubrication. a large amount of metal is generated over a short period of time, in this case, only a few hours. And the contribution of these particles in all the bins has exceptional decay. This debris is being generated suddenly and without any kind of warning, and that stops generation. Now, these systems, they catch these things quickly and allow for some turbine shutdown and prevention of any kind of catastrophic damage. This example, we're looking at the bearing spall. Here, large amounts of metal are generated in a more regular manner with increasing amounts of debris, but the particle size doesn't increase. The contribution of particles in all bins actually exhibit an exponential decay. We compare this to gear liberation example prior. Well, this one's a slow buildup as the fault progresses. The OEM vibration system did not pick up this fault. Here's an example of the spinning bearing. Once again, the OEM vibration couldn't pick this up. This system is the only system that can find that spinning bearing. Multiple discrete events of these small bursts of metals over a short period of time frame, only a few hours in this case. It's a contribution of particles in all these bins with greater weighting and smaller particles. Now, this could possibly be correlated to large ambient temperature swings. Here's an example of the planet carrier spinning and pinning repair. Large amounts of metal are generated over a period of time. Now, post-pinning operation, the wear generation drops off dramatically, and that's after the detection occurs. Not only can Poseidon detect the fault, but monitor the success of the lower cost fix over time. Here's an example of remote oil health monitoring. In this case, you see a rapid degradation of oil, and that can occur due to contamination, leaks, etc. It can damage equipment before the oil samples actually are taken or even returned from the oil analysis lab. Real-time detection of the oil degradation is possible. An algorithm is detected the slope change and creates an alarm. This leads to an immediate inspection and then an oil change before any kind of further damage can occur with that asset. Lab samples taken every 6 months or so, they won't catch any kind of contamination or this kind of damage. Now, here's a real-world example of online oil condition monitoring. This takes place over a year, and quite frankly, the data is pretty boring. The sensor's installed in a gearbox and was filled up with AMSOIL PTN 320. After about a year plus of operation, no parameters nearing the condemning limits are seen. Indicates very little change in the oil health. No appreciable health change. Now, we're using high-frequency bulk impedance. That's typically sensitive to contaminants and oil additive depletion. We also look to use percent relative humidity. That's a much better parameter to track water than parts per million. Here's a case study using the smart breather technology. And here the challenge has been that desiccant life degrades at different rates on different turbines. Replacements are typically based on time, though. A solution? Well, using a smart desiccant breather. And desiccant breathers can be replaced based on condition and not time. So here, instead of using a preventive maintenance approach predicated around a schedule, we're implementing predictive maintenance strategies. Now, some breathers they can last up to 2 to 3 years, while others only a few months, depending upon the climate and the environment. This example, well, we're taking a look at wind turbine gearboxes side by side on the same wind farm, able to reduce breather usage and increase breather effectiveness. I want to share with you a bearing monitoring device, the Midas ferrous monitor. It's an on-site portable ferrous concentration measuring device. It provides fast, instant on-site identification of bearing faults. It's low cost and portable. It's a benchtop solution. It's cost-effective, accurate way to track grease wear debris on main, yaw, and pitch bearings with immediate results. These instant results are on site, repeatable and accurate for the ferrous concentration down to a single part per million level. Can increase sampling frequency due to this portability and low cost. Allows for increased sampling to track and trend over time. It's a way to detect failure early on. You can detect failure early for reduced downtime and operation and maintenance cost. Comes out to be about less than a cent per sample. Now, there might be some older wind turbines out there that don't have fiber to tower or Ethernet to up tower connectivity. In this particular case study, Poseidon developed site-wide wireless network utilizing LoRa through a single wired or cellular connection. It's one communication system for one cellular device. Validated to a 6-mile radius, a 12-mile diameter of line of sight. Currently, there are 2 operating in the United States. In 2020, there'll be greater than 250 installations. The picture is an example of that current installation. Now here's what the configuration would look like for the LoRa. Here we have our sensors. They're going to be sending information via Bluetooth or even wired. That information is then transmitted through a cellular tower where the data is collected, connected, then on to options for analysis. I want to thank you for your time today. Just to let you know, there's a better way to monitor your turbine. Right now, I'm going to turn it over to Stephen Steen for some questions and answers. Thank you very much.